everyone, and welcome to today's webinar on non-contact bridge roadway tunnel inspection adapting to the new normal, presented by the IRS Committee on Asset Management. Wherever you are and whatever time it is, thanks for your participating. My name is Mohammed Sayyar, and I'll be hosting today's event on behalf of the Road Asset Management Committee. We have an exciting webinar today covering a topic that is important to all road and transport agencies. First, a few housekeeping matters. As is typical of IRS webinars, today's event will include a question and answer segment after the presentation has concluded. All attendee microphones are muted, but we still want to hear from you. Please type your question into the questions area of the control panel on the right of your screen. I will sort the questions and address them to our presenters. They will answer as many as time permits at the end of the presentation. We expect today's webinar to run for approximately 60 minutes, including Q&A. If you have any questions or a comment not related to the presentation, such as technical issues, please use the chat area and send the message directly to the organizers, and we'll deal with important issues immediately. All IRS webinars are recorded, and all registrants will receive a PDF of the presentation as well as a video recording of the entire webinar. Additionally, all IRS members have complimentary access to the entire archive of IRS webinars, and non-IRS members may rent any of these titles. If you're not an IRS member and are interested in hearing about the benefit of joining, please contact me or Majid at the end of this webinar. With the technical details out of the way, we are ready to begin. To guide us through the use of non-contact bridge roadway tunnel inspection adapting to the new normal is Masato Matsumoto, President and CEO of NEXCO-West USA. He's the recipient of the IRS Flowship Award, which helped more than 1,404 students from 118 countries enhance their post-grad education. For more information about that, please visit us at irs.global. Gentlemen, the floor is yours.
Morning, everyone. Welcome to IRF webinar. My name is Masato Matsumoto. I'm the President and CEO for NEXCO-West USA Inc., IRF member company. And today I'm happy to be here to present our experience with the non-contact bridge roadway tunnel inspection and adapting to the new normal. So I am with my colleague here, Mr. Kyle Rusky, as a co-presenter, and he's going to present our case studies after my introduction. So under the pandemic situation, we've got to adapt to the new normal situation for the construction and infrastructure industry. And even under the pandemic situation, the inspections of structures, bridges, roadway, and tunnels, they cannot wait, and we still need to do bridge inspections and tunnel inspections under this pandemic situations. But traditional visual hands-on inspections require significant field hours, and that makes it difficult for inspectors to secure social distancing. Because a team of inspectors need to be in the field together and with the close distance, and they have to spend a lot of time in the field. So it's a challenge under the new normal situation. So these pictures on the left-hand side are the people who are dragging chains on the bridge deck, or applying the hammer sounding, or rappelling by the rope for the underside of the bridge inspection. And so these traditional way of hands-on and visual inspections, they need a lot of man hours in the field. But if we could replace part of the field hours by the remote, very quick camera technologies to detect the cracking, spalling, or any other type of defects on the concrete structures, that would be great to adapt to the new normal, in order to reduce the man hours to be spent in the field. So the idea is, the field data collection can be done instead of people in the field or on the bridge deck, but we can mount the camera on the vehicle and we go with the vehicle with the highway speed. So we don't need to gather on the bridge deck, but we just drive on the highway without any lane closure or anything. We just take the data in the field from the vehicle. Then we bring the data back to the office, or we can currently, remotely work from home, and we process the data collected in the field, and we prepare the deliverables, or deficiency notations or a deficiency maps, so that we can deliver the the deliverables for any type of defects, cracking, spalling, delamination on the concrete structures, and we host the web-based deliverables, so that we don't even have to meet to report the deliverables. So these are the application case studies for bridges. I'm going to pass it to my colleague, Mr. Kyle Resky, to talk about our experiences for the bridges and roadways and tunnels.
Awesome. So we're going to start off with bridges, move into talking about the deck top and how we typically inspect bridge deck tops at NEXCO here, and how that fits very well into the current pandemic scenario. So right now, some widely used techniques to evaluate bridge decks include chain dragging, taking a chain across the deck. And of course, this requires closing the target portion of the deck that's being inspected. The same with hammer sounding. So physically tapping on the deck and listening to hollow areas. The visual inspection, which may involve sketching and note-taking, all of which require direct access and long, prolonged times for the labor hours. And so this is all meant to satisfy MBI, OSHTO, and other client specifications. So yeah, this is kind of the current scenario. And this is typically what your chain dragging operation looks like. And you can see the guys are progressing very steadily and listening closely to hollow sounding areas in the deck. And even sounding rods are used. Kind of just walking slowly across the deck and listening to those hollow sounds. And so I'll pose the question and continue to think about this question as you listen in. How long would it take to inspect a 5,000 long bridge deck? And let's say maybe with a couple lanes, like a northbound and a southbound lane with some shoulders. What techniques would you use? What would be representative areas that would be looked at? What would the lane closure procedure and the work zone safety procedure look like? And how many people would it require? And of course, considering the pandemic situation, what kind of proximity do those people need to be in? So the alternate proposal here is to essentially take away that initial lane closure, scan the entire deck, and get a very good picture as to the deck condition with visual and infrared technology. And we do this with our desktop scanning system. We call it DTSS. And maybe if you've heard of the DTSS system before, maybe you can type in the chat and say yes, or put a smiley face or something. And so the benefits of this system are, of course, the absence of the lane closure. Not only that, but the system being used is adaptable to traffic conditions. So this means that no matter what speed limit you're going at, from anywhere to 0 to 70 miles an hour, this thing is going to take a consistent and objective data set. And of course, the imagery taken is objective. It's geolocated so that any deficiencies found can be very easily referred to. The whole operation is done within a vehicle, so you simply pass over the deck while the sensors are turned on and recording. So we consider this much safer for inspectors. They're not exposed to unsafe highway conditions for prolonged periods of time, which hammer sounding and chain dragging do require. And at the very end of this, you're going to get a comprehensive deficiency map. And we use the terminology deficiency map to refer to our deliverable set, and we'll show you some examples of that. So to talk a little bit about the technology, the two main components involved in the mobile scanning procedure, infrared can be used to locate any kind of temperature differential in the deck, namely temperature differentials created by delamination. So these are instances of debonding in the concrete that you can't see with the naked eye usually, but infrared can during times of temperature change in the day or the night. And then to capture the nitty-gritty, the cracks, spalls, and all of that, we use line cameras. And this essentially enables us to use this method, period. The line camera technology takes out a lot of the distortion factors associated with your regular area scanning camera like you have on your cell phone. That's not actually giving you an inaccurate picture per se. It's not scaled. But with a line camera, it is. So the imagery we get is not only crystal clear, it's scalable. So it means that the deficiencies that we see in the maps we generate are to scale. They are the size of the deficiency. And so this is the couple shots of the system in action. You can see the rear mounted line cameras and the infrared camera. And the little shining light that you can see in the rear of the vehicle is a speedometer that sends a pulse to our main computer system, and it controls how fast the cameras record. So it's all quite easy. And these inspectors and this laptop, they're all inside the vehicle at the time of data recording. So nobody's getting out on the side of the road and using chain dragging or hammer sounding or up close visual techniques. That can be saved for later in our mindset. And so this is kind of a shot of what you get directly from the recording. On the left, you see the raw infrared images. So this is what you typically see when you're looking at infrared data. The middle is an automatic detection function that we use. It basically looks for anomalies in the temperature data and pronounces these anomalies. So we can very easily find potentially delaminated areas. And then we need the HD visual, as I mentioned, to detect cracks and spalls, but also as a proof for the infrared image, because if anybody on the call here has used an infrared camera before, sometimes it plays tricks on you. So things like the shadow in the upper right-hand corner of this image, or discoloration, oil spills, stuff like that, will create this kind of splotchy temperature differential that's not necessarily a delaminated area. All right, so the first case we have two past projects that we're going to review. This one was done on a network level basis, and this is really what the DTSS is designed to do, because you're passing over potentially multiple bridges in a single day to take any amount of square footage of target bridge deck. So this particular project was done in the state of Virginia, where we happen to be located. It was done for the Virginia Department of Transportation in 2017. 20 target bridges were picked out for us, and we drove across the state and gobbled up the data for these bridges in about 2 weeks. And had the bridges been on the same roadway or same kind of like road system, then it might have even taken a couple of days. And so we generated per bridge a infrared deficiency map and a visual deficiency map. So this example was a 2-lane bridge, and you can see our raw infrared image on the top and that automatic temperature differential detection on the bottom. And then based on the infrared data and the visual data, we looked into the full area of the deck. And actually this is a different deck because it's 4 lanes, but we picked out the exact area of each of the deficiencies. And so you can see these yellow markings are either minor spalls or delaminations, and we classified them as CS2, condition state 2 findings. The red, either unsound patches or major spalls, were classified as condition state 3. So this is kind of a good way to get a good overview of what's happening on the deck and quantifications from it. And so the real idea we want to put forth with this system is we pass over a deck, we generate a deficiency map, and then what happens with this? We want to identify structures and certain spans on the structure, or areas on the structure that are in need of repair or further attention. And so this kind of information can be filtered back into InfoBridge or whatever asset management software is being used in the form of the deficiency map data and inspection reports. So these objective reports, we're getting the exact area location of deficiencies. We know what spans are in critical condition. And with follow-ups, with a data set like this, every 2 years that an inspection is taken, we get a better picture about the progression that this bridge is following into. So, for example, if we take this bridge in this year, 2020, and compare it to the 2022 and 2024 data, we see a progression, and we see which spans are in need of attention. We see, what deficiencies are prevalent for a certain bridge. So we get a very, very powerful planning tool by using this mobile scanning method. And with the COVID-related benefits, there are also these inherent benefits of about 20 to 30% of total project cost saved, which is pretty good. And this is kind of a number that we came up with by looking at what a normal contractor would go through with a typical bridge deck inspection, keeping in mind, kind of that like your typical vanilla 5,000 foot bridge that I posed in the beginning of the presentation. So we looked at all the labor hours it would take to do the visual, to do the hammer sounding for the entire deck, and kind of cross-compared our cost. That's what we got. It reduces the impact on road users because you're not shutting down a lane initially. You can shut down that lane to look at the specific area or the specific span that is in need of attention, but only that span. You don't need to shut down, the bridge for a whole week. Maybe you can reduce it to just a couple hours. And then it helps with the tracking the progression in the deterioration. So you have, time A and time B and comparison between the two. And objectively, you can see clearly how the damages are progressing. And it's social distancing friendly because the two workers that are in the vehicle, sitting in the back seat and the front seat, they're not getting out and interacting for a long period of time. So we think it's a better alternative. All right, so I'm going to transition into bridge components. So these are the piers, the box interior, the bridge underside, which typically require some kind of very special and complex access procedure. And we're going to jump right into a very representative case of how we can reapproach the initial analysis and inspection of bridge components, especially for complex bridges like this one. So unfortunately, Mr. Mohammed Asif was going to join us today. He was the project manager for this project and works at AI Engineers. And we worked very closely together on this project, and unfortunately, he was unable to make it today. But we scanned the Pearl Harbor Memorial Bridge located in New Haven, Connecticut. This was just last year. And we used the desktop scanning system for the desktop, and then two additional systems that I'll introduce now, the ACS and the U3S. And the exterior of the bridge totaled in about 1.5 million square feet, and then the interior about 2 million square feet. So it's a very large scale project. And those surface types, the deck top was one story, and then the other bridge components, the box girder exterior, the girder interior, the tower exterior, the tower interior, all had to be done in a non-mobile manner, right? We couldn't hook up a camera to a vehicle and just pass through the box girder interior. That was not an option as of yet. And so we were required to locate and map all cracks over 0.3 millimeters. And that's pretty small, right? So we needed to integrate a high definition imaging solution in this kind of complex environment. And so how we approached the work was, all right, we're going to take a comprehensive crack map and then basically quantify everything crack by crack in a quantitative table. And all findings above 0.3 millimeters are going to be recorded. AI Engineers, our client, was going to, or they did, validate the crack detection method by taking 5% of the total surface area and visually inspecting it afterwards. You can see that on the right-hand image. We also needed to categorize the crack types based on the bridge inspection manual. And so these type classifications were based on what kind of structural crack we were looking at. And then we needed to review and edit and tweak the automated crack detection functions we were using to make sure that it matched the previous year's inspection report to a large degree, and will be set up to, as I was speaking about before, look at the progression of future year reports, make it comparable to the 2021 inspection. So the DTSS was used for the deck top. We've gone over that. This is kind of what the results look like. We changed our typical legend a little bit to satisfy client requirements. And just to note the accuracy of this, the validation which took place on the deck top also took place for the lamination detection, not just cracks. So this, in this very large deck top of about 7 traffic lanes, we were able to point out areas of the lamination to this degree of accuracy, so that the lamination that was detected right next to this patch here was found in the field, was verified, and it was there, and it was to size. All right, so the box girder exterior, the underside of the bridge, was imaged with a high definition camera and IR camera from a boat, and we did this through either this little safety boat or a barge, and the barge yielded the best, clearest data because it was very stable, and so we were able to get very crisp data from that. So the imaging systems we used to get this exterior and the rest of the components was the U3S #1 and ACS. So U3S is some kind of combination or setup of a digital camera and an IR camera. It could be on a tripod, a harness, or a cart, whatever the site, whatever is most efficient for the site. And the big bonus from this, and what we want to communicate with this system, is you don't need a boom lift or a snooper truck. So the actual imagery data you're getting is so clear, and the shape and the width of the cracks are so defined that this can actually generate a map of even cracks that are very hard to identify when you're up close in person and visually confirming it. Sometimes you'll need that visual confirmation, of course, but you will know which are the specific locations you need to go back to for that visual confirmation. ACS is very similar. It basically operates on an automated platform, orients itself to take a series of pictures and then stitches it all together automatically. So it's a very easy to use system, also generates very high definition visual data. And so this is kind of an example result that we got from the box girder exterior, or the underside of the bridge. And you can see on the top of this map, you have the individual boxes themselves, or cells as they were called. And everything is to scale right on the original plan. And we noticed certain patterns by locating these cracks in the exterior, such as transverse cracks in the wings, and longitudinal cracks being pretty representative for the soffit. And then moving into the box girder interior, and this was difficult because of the tendon ducts that you can see on the left-hand side. We needed some kind of way to image consistently and stitch all the imagery into a map. And so we either used a tripod mount or a cart mount to do this. And some of the wing joints were a little cramped. So this is an example of how we took the walls and diagonal surfaces in those joints. And this is a typical the wing cell deliverable generation. And to give you an idea of what the crack detection looks like in here, we've got a scale within our proprietary software that we can kind of reference as we go through. So you'll get an automatic mapping of the surface, and then we can double check how this automation is going by manually looking at the scaled width and such. So for the piers, which were kind of separated into towers and columns, we used U3S as well with quite high resolution camera, and generated very similar results. The piers had quite significant cracking patterns, and just to show the capability of detection, even the sheer number of cracks that was detected here could be noted, and we had to essentially identify and label each individual crack. So that was done. All right, and then this is kind of a close-up of one of the towers. And all this was put into CAD. And I'm going to show you a little bit more about the deliverable outputs in CAD and how we can host this online. And the online hosting bit is very important in the COVID situation. For the tower interiors, we need to use a little bit of a unique system. And I think this is unique to us. I haven't really seen any other company use this pulley system before. So basically a camera is hosted in this box, and it's lifted up and down in increments, and basically turned in a 360 rotational direction, and individual images are taken and basically stitched together into one comprehensive map. So this is kind of what that looks like afterwards. So the interior of the column is kind of like splayed out. And one thing that we were very happy about is in both the box interior and the column interiors, the requirement, the width requirement was 0.3 millimeters, but we were able to detect down to 0.2 and occasionally 0.1 in some cases. So we exceeded the detection requirement. And the crack summaries were essentially organized in summary sheets by crack ID, the structure name, the element, the division. So despite the complex nature of the bridge, they were all organized into comprehensible sections. So you could see in this construction segment, how many cracks am I seeing? What structural classification type were they? And what was that total length of cracks and the average width of cracks in this section? And as mentioned, the client, AI engineers, went back into the field after we generated the data, and they took a look at the accuracy of what we did. And both parties, all parties involved, were very pleased. because the average accuracy was in between 85 to 95%, mostly on the 95% side. So, and these are millions and millions, or thousands and thousands of cracks we're looking at here, and about 3.5 square feet, to 3.5 million square feet of area analyzed. So to have a 95% accuracy rating on that is, I think, pretty impressive. All right, so we're going to walk through what the deliverables look like. And just to note, this is all online. So anybody can access this with a username and password login. The data is perfectly secure because it has the username and password login. And you can see, zooming in here, the image quality is quite good. The raw data for this file, even in most files, it could be anywhere from 30 to 80 gigabytes because we're using very high definition images. But you notice we're accessing this very fluidly and very easily. And that's thanks to similar technology that you'll see with navigation software like Google Maps. It's called pyramidal loading. So it only loads the section of the images that you really need. And so when you zoom in, you're seeing a high definition version of that section. And so you notice, and actually I'm going to go back and highlight this point here. You notice the guy clicking on a plan here, picking out an individual column in the bridge map. And so we kind of segmented the bridge into its different components, and you know, all you need to do is just click on what element you want to view. For example, the anchor pier. Click on that pier, and then it pops up with the result. And so we think that this kind of easy access to the data is great for structural owners because you don't need to be at the office. You can be at your home with your kids, sipping on coffee and you know, looking at all these cracks in the meantime. So I think it's a great way to be closer to the data, and you can see how fluidly the demonstration is zooming in on the individual cracks. This sample shows different surface view types. So this is the box interior. It's kind of segmented out into the various cells. And this file in particular is a big 80 gigabyte file. Yet we are zooming in and viewing these efflorescence cracks with pretty good ease. So it shows that even a complex structure like the Pearl Harbor Bridge can be organized efficiently. And it can be shown in a way that it's easily reviewable. I'm going to skip a little bit here. And here you can see, if you don't want to go through the like this kind of navigational section here, you can just pick out an element or, you know, a particular structural segment and just open that. We've also got the capability to download into CAD. So right here we're downloading a CAD file, and you can see on this file that we've directly downloaded from online and it's got all the crack shapes, labels, everything basically the same, just no picture. So, I mean, imagine, typically these cracks are notated in the field, and then somebody has to go back to the office and draw them in CAD again. And there's no kind of like skilled imagery that comes along with this file. But having both that CAD set and then the image file, I think does a good job for setting yourselves up for the next inspection and comparing and contrasting to that inspection or the previous inspection. So if a similar data set like this were generated in 2017, we would see in 2019, which cracks jumped the width the categorization threshold, which increased in length. What patterns are we seeing in 2019 but didn't see in 2017, and so forth. And then the last type of output that we generated here is just a CSV. It basically tabulated all the crack data and separated it into different kinds of classification. And you can see we highlighted in white and left in green different types of cracks, like efflorescence cracks or insignificant, moderate, etc. So they were pretty clearly color coded, and a length and width value was given. So the next kind of sexy deliverable we generated for the box interior and the various other structural layers was a layered deliverable, which it basically projected the deck top, the box girder interior ceiling, and the layers, the box girder interior floor, and then the exterior soffit, all on top of each other. And so this was requested by the client because it was of particular interest to find through cracks and paths that water was taking into the box interior. So if we view this next video, you're going to see the transparency for the deck top kind of fade into the box girder ceiling. So you can see here kind of an advanced section of cracks, and then in the box girder interior, more cracks. So what is this pattern telling us is, is water ingressing in this way? You can start to kind of question these observations. And so cracks with efflorescence on the ceiling could signal that water is coming in or has come in from the deck top. And then you can go back up to the deck top and see where that was. All right, and I can't stress enough the importance of having a scaled and then high definition imagery set. Even simply the CAD outputs generated from the imagery for future accurate comparisons in the future. Yeah, and then what does the future look like, and what decisions we should be making for given the patterns that we've seen over these 2-year periods. I think that we can get a better picture of that by generating these deliverable sets. All right, so we spent a lot of time on bridges because that's kind of our bread and butter, but I do want to cover roads and tunnels just briefly. And so roads are mainly satisfied by our Smart Eagle system. So this system uses a set of lasers and a 3D triangulation camera to detect cracks, IRI, other various pavement measurement indices. So these are the indices, the IRI, PCI, rutting. This is done through horizontal and longitudinal road profiling. And then we also get a set of visual imagery from the 3D triangulation camera, which is essentially kind of like a beefed up line camera. It operates very much like the DTSS in that it can go up to about 55 miles an hour, anywhere from 0 to that, and then simply pass over the target road section and you've got your data. So what do we do with this data? And that's kind of a big question that a lot of road owners are asking. We have a analysis platform that we use online. So we'll take a look at the target road and mark out deficiencies as we see them. That result is going to basically be either on a grid basis like you see here, or kind of like the deficiency map basis that we see in the DTSS. The findings are located, quantified, and then the beautiful thing about this platform is you get the pyramidal loading just like what I showed you for the Pearl Harbor deliverables. And because the analysis is done online, you get the results of the analysis as they are done. It's live. So for example, if we took 10,000 miles of roadway data and our analysts were going through the data, they may generate 1,000 per week, or whatever the value is. And the road owner doesn't have to wait for them to deliver all 10,000 of the miles. They can look online and see what the analysts have done that day, that hour, and start making decisions. So they don't have to wait until a report has been generated a month later. They can start taking a look at maybe the first 1,000 feet of the 10,000, first 1,000 miles. All right, and then moving into tunnels, we've got our tunnel scanning system. And this system uses an array of line cameras and infrared cameras and a 360 camera to capture information about tunnel liner. This was not done in COVID times, but we think it still fits the point that we're creating here. We don't have to shut down a section of tunnel or route trains in another track. We can just go on a high rail vehicle, pass through the section of tunnel within the access time granted. So these are the components that we'll typically set up for the system. We've got the line camera and LED arrays. The LED, the lighting is very important for the system because you've got no light in the tunnel. So that span of light is generated, and you can see that very clearly in this video. So that white span, as we're passing through this steel liner, is where the data collection is happening. I love that video. And so this is what the data looks like when we're done, very similar to the DTSS and the Pearl Harbor maps. you've got your scale map, and then with that, you can kind of see where the leakage is, right? So whether it be steel or concrete, you'll have instances of very cool temperatures where active leakage is occurring, and where potential leakage or buildups is occurring as well. And so this is kind of an example of some water infiltration that we found during a particular project. Some previously repaired leaks, but they are leaking again. Efflorescence. And we've noted with the efflorescence that there is kind of a temperature differential in active and passive efflorescence. So the efflorescence that is still growing and there's still water ingress, we're able to pick up on it because of the chemical reaction that's occurring. And so that's kind of a useful trick that we have come across after taking some data sets. And then overheating of electrical components is also quite applicable, because it's a classic IR application, and we're still taking that data at the same time. So it doesn't have to be a 360 degree recording. We can basically furnish any amount of infrared or line cameras to match the contour or match the target area. For example, if you just want to look at the grounds or just the crown, we can reduce or increase scope as needed. All right, so that is pretty much it. We want to move into a question and answer segment here.
Thank you, Masato, and thank you, Kyle, for such a wonderful webinar and a wonderful job articulating this important topic.